Hi there. Thanks for checking out this video abstract for our paper, Mitigation of GNSS Cycle Slips Due to Scintillation Using Radio Backpropagation. I'm Brian, the first author of this paper, and my collaborator is Dr. Jade Morton, who I work with at the University of Colorado Boulder. This paper is motivated by the impacts of ionosphere scintillation on GNSS. In particular, equatorial plasma bubbles are known for causing diffractive scintillation that is associated with deep signal fading along with carrier phase fluctuations and cycle slips. One such example is shown here for the GPS signal bands. The event lasts over an hour and demonstrates how intense fading can occur simultaneously on all signals. The erratic behavior of the carrier phase, shown in the bottom panel, is largely associated with the occurrence of cycle slips, which are detrimental to various applications that use carrier phase, such as precision agriculture or space weather monitoring. Overall, the cycle slips can cause meters of error in carrier phase-based relative range measurements, and up to tens of TEC units error when estimating total electron content. So it is important to identify different ways we can try to address cycle slips in GNSS phase measurements. In this paper, we consider a physics-based phase screen model that describes how scintillation develops. It assumes that signal propagation through the ionosphere can be reduced to plane wave propagation through a single effective phase screen located within the ionosphere F region that can be modeled using stochastic parameters. An example of a simulated received signal is shown on the right, with amplitude in the top panel and phase in the bottom panel for GPS signal bands. In this simple model, there is one key parameter, called rho over v effective, that encodes all the information needed to reverse this propagation and obtain the complex signal at the effective phase screen, back before the diffraction effects have developed. The basic idea of this paper is that if we can guess or estimate this parameter, we can use backpropagation to produce a smoother signal that has no or significantly fewer cycle slips. In the paper, we provide results on applying this technique to both simulated and real data. We use simulations to assess the impacts of noise and Doppler uncertainty, and with the real data, we demonstrate a reduction in jumps in the ionosphere-free phase combinations. Together, our results suggest that this technique can be effective at reducing the impacts of ionosphere diffraction and cycle slips. As for other key takeaways, this approach does not need multi-frequency measurements, so may be particularly useful for single-frequency users. Also, the algorithm is currently designed for batch processing, but trying to adapt it to work for near real-time application is a good topic for future research. Thank you for checking out this video abstract, and I hope you find this paper to be interesting and useful. Take care.